So I think this is the image of Friedrich. I don't know if this is the right position here. But this is just the generator, right? You can see it's in the back. So this is just to I'll be very fast on this one. Sanjay mentioned about the classic approach, the present approach with the FADEC, and sensors linked, individually on 2 wires or even a dot for pressure sensors to the FADEC. This sure it has some, disadvantages as a method. Moreover, the fact that this system would not allow, in a simple fashion, active control, because now from sensor and actuator, I have to couple them through the FADEC. Would be delay times, would be so many significant disadvantages. This is the concept. The idea is to go with basically a network with a bus on which smart sensors and smart actuators are, linked. Each sensor or actuator is an address, so they could be removed and substituted by some other sensor that is similar in capability and has the same digital command or input-output. So that is the main idea of sensors. Now, to say sensors, why don't use the other sensor? We need smart sensors because the electronics has to be somehow migrating towards the sensor. Sensors, you know very well, they are transducers, and there are various levels of electronics implementing sensors. There are one-way communication, two-way communication, adaptive sensors. They basically could modify the gain in the sensor from command from the outside to compensate for temperature, whatever, drift, and so on and so forth. So in these classes of sensors, smart sensors are part of those, in which you could do processing directly on the sensor, and eventually pass further on just the okay or it's not okay. Or if it's not okay, what measure could be taken in order to adjust the specific change in the performance as planned. So this is the sensor for distributed control. The idea is that each sensor from the previous scheme, it's substituted by a smart sensor or actuator. We talk about sensor actuator in a generic fashion. Signal processing is done by these smart modules that are attached with a sensor or the actuator. Information is transferred to a bus, right? And the smart module would include processing and even capability to perform some health diagnostics and eventually manage functions. So that is sure a long way to get in there, but once this sensors like that will be available for the specific applications that aerospace needs, then probably the task would be a little bit easier. You might say, we have sensors like that. There are many market sensors, but again, they are limited as temperature, reliability, even capability, measurement range, but they are available. They are sensors like that. And I could mention just, the accelerometer, probably the first commercial success of MEMS, of analog devices, the XL50, that it's there on the market. It has all the electronics included. The sensor is very small. But again, 50G, even 250G would not do it for the engine. We need probably much more. It's one about, talk about vibration, higher frequencies, and probably a little bit more G. Advantage of distributed control, weight reduction. Although this is disputable, we might gain a little bit of weight if, I should say, we have a large engine, because under the provision, the number of sensors, although smaller, they have to carry the electronics, so that it's, basically the mass is distributed more than before. Cost reduction, this is again under the question mark, how can I get a cost reduction? Definitely if I have a mass production, if I buy cheap, right? And who's going to sell for low cost? Someone who makes a mass product, as a mass production, is capable to disseminate the product at low cost. High modularity, that's a big advantage, because again, the advantage is that I would not need to go for qualification of the product, because I could qualify only the module that I'm going to change. So given the interchangeability of the system. Distribution of the computational burden could be, it's a good point, because now everything occurs into the FADEC. Now, if some sensors will take the burden of the computation, I could basically increase the response time, improve the response time, not increase, improve. Obsolescence mitigation, it's a very serious point in here. As long as new sensors appear on the market, I don't have to stack them and be able to perform maintenance with the old technology. I could intervene on new sensors as long as they have the same basically communicate interface, the same type of interface.
But on the other hand, doesn't it slow down the innovation, the modularity? Because if one module is developed with another technology, it's no longer compatible.
You could look in this way, but if I have to change a module, because that is the only obsolete, I could do only that module. I don't have to go to requalification of the entire product. That is very expensive. I could requalify the module and just plug in. Remove the old one and plug in, as long as I have the same interface.
Actually, modularity increases the innovation capability, because supposing I'm buying a sensor from company A and they have a means of using a particular diaphragm to measure the pressure, and then somebody else comes up with a new technology to measure the same variable, which is more efficient and cheaper. Now, as long as they have the same technical interface to put into the system, you can use that one.
Yes, but sometimes the interface is slowing down the process.
What he says is, to some extent it makes sense, because if you use an operating system that is, now operating systems in vehicle in general, and they are very simple. They are not, they don't run Windows or something, and they have to reboot, and extremely simple, and the communication ports are well established, and it's not a big improvement to doing the car operating systems are same. CR5, and they operate for 20 years. The same operating system, nobody touches, because it's very good. It's doing the job. It's the point. Same reason. If you see obsolescence here, sure, then it's the same thing for FADEC. FADEC is obsolete, right? You still have taps of copper tube, and what you do with those, right? So, but indeed, it's an issue in here where you have the system and you'll be tempted just to. But again, the operating system usually is dedicated, and it's properly designed to make sure that you minimize the errors, and minimize the failures. So this is the advantage use of open system standards, and in that case you don't have to requalify. Scalability, basically redistribution of the computation. If some module works very hard, could transfer some of the computation to another module to make sure that the system responds in a shortest time or in real time. So what we expect from smart sensors, we need some form of self-diagnostic, self-adjustment, calibration, and eventually compensation of drift or temperature compensation for environment in general. And it's very important also to communicate only the meaningful signals with the central power central unit, right? The meaning of each of the above, that means self-diagnostic, self-adjustment, calibration, may be different for different classes of sensors. Smart sensor might also include some advanced communication means, protocols that would enable self-communication, self-test. The constant of the sensor is transmitted automatically because it's retained somewhere in the memory. So that will facilitate basically interchangeability fast and immediate. Right? Challenges for smart sensors. Yeah, always is temperature. In all the applications related to gas engines, gas turbine engines, the limitation is temperature. Basically, for electronics, standard electronics operate between minus 55, as a matter of fact, to 115, and military application, minus 65 to 155. So there will be, it's a standard for operating for electronic components for any type of component. When this condition's been established, that was a long time ago, I think it's until 8081 or something like that is the standard. And that was based on the vehicles that are in the combat, and they have to be either on very cold climate or very hot climate, where the sunshine, hits the vehicle is enclosed somehow, and temperature could go inside up to 115 degrees. That's it. They didn't didn't take into consideration capability to go inside the engine and check how the burning is going on. So this is the basic requirement for. We know also that there are transducers. I'm saying transducers because they are not instrumented with the electronics next to the sensor that operate at higher temperature. In the case of electric pressure sensors, there are few. Radio frequency, I think, sensors, but the still temperature at which they can operate is bounded at 750 degrees. There are a little bit of a problem there with the temperature drift. I mean, the sensor drifts with temperature eventually after a number of start-stops. But they are still there, and they are very good for test rig operations. However, they are not very much of them, not very many are used in engine directly. The RF, I think they are used in the fighter, right? Euro fighter. Some adjustable design feature basically could be selected and might enable installation of such sensors that operate at, 155 to phase 200.